Okay, so I wanted to do some examples of how to use this folding diagram. So let's suppose that we have three cases here. The signal is 80 hertz, and the sample rate is 100 hertz. And the second case where the signal, not fig, signal is 100 hertz, and fs is 60 hertz. And then the third case has the signal equal to at 100 hertz, and the sample rate is 250 hertz. Okay, so here's the solution to part A. Okay, so the Nyquist rate here is 100 over 2, so it's 50 hertz. And so if we look at the fraction, if we have f sig over f Nyquist here, we get 80 over 50, and that works out to be 1.6. Okay, so now I'm going to go back to my folding diagram here, and I have 1.6 here, and I go down to 0.4. Okay, so the aliased frequency, FA, is equal to 0.4 times Fn, and that ends up being 20 hertz, right? 50 times 0.4, 20 hertz. Okay, now for part B, Nyquist rate is 60 over 2, or 30 hertz. So f sig over the Nyquist rate is 100 over 30, which ends up being 3.33. And so now we go back to the folding diagram here. And it's actually not here, but we can sort of imagine where it is, right? This actually ends up being 3.3. Okay, so it's going to come down like this. Okay, and well, mathematically, right, if we wanted to write the math here, this ends up being, like you could see that this is at 4 minus 3.333, ends up being 0.6667, I guess, right? Right, we'll just round it off. I mean, 3 decimal places is enough. Okay? And so when I multiply 30 by 0.667, I get 20 hertz. Ooh, the same thing. Haha. So you see that in both cases A and B, right, depending on the sampling rate, both of these sine waves, both of these signals, one's at 80 hertz and the other one's at 100 hertz, they both get aliased down to 20 hertz, so they'll look identical when we record the data. In the last example, the Nyquist rate is 250 over 2, 125 hertz, and we see that the signal is 100 over 125, and so that works out to be 0.8. Okay, and right, if we look back at the folding diagram, 0.8. Or maybe I should do them. I'll do this in the second color. 0.8. Okay, so it ends up being there's no aliasing. Right, because the signal frequency is already below the Nyquist rate. Okay, no aliasing here. So let me go back to this folding diagram and I'll label them. This is B, this is A, this is C. Okay, so that's how you use the folding diagram. And I'll give you a blank one in case you want to have one. Let's say for an exam or something like that. Hint, hint. There you go, your own blank folding diagram. So just to summarize things, here. So for spectral analysis, we want to make sure that we choose Fs to be greater than or equal to 2x, the maximum frequency of interest. Right? So at least more than twice the fastest signal that we expect to record. And usually quite a bit more, maybe 4 times more. The other thing is that in terms of the number of points that we use in calculating the spectrum, number of points used to calculate. Okay, remember when I showed, I'm going to go back and give you kind of a concrete example of what this is. So you remember when I showed you this sinusoid, right? I showed you a sinusoid here and it's sampled. And I showed that I took a record that was 1 second long. So that corresponded to 100 samples. Okay, so that's what this n is. So how did I pick that number? So it turns out that the frequency resolution of our spectrum, frequency resolution, which I'm going to call delta F, is going to be equal to the sample rate divided by the number of points. Okay, that's the smallest incremental frequency that we'll see in the spectrum. Okay, and so I'll go back to, again, to that example on the slide. And so this was 100 points sampled at 100 samples per second. And so delta F is Fs over n is 1 hertz. And so if you look at the spectrum that I have here, I basically get 1 point in the spectrum at every 1 hertz. So I can see a sign at 20 hertz and 21, 22, but I don't get measurements that are in between. Now it happens to be that if I had a sinusoid that was at like 20.5 hertz, I would still get a point in the spectrum, but it would be sort of smeared over a couple of points in my FFT. Okay, so usually we pick a spectrum. We pick that that resolution, that delta F, to be fine enough to observe. Like if we want to see closely spaced signals, we'll choose that delta F accordingly. Okay, and you could see like way back, actually going back to the data that I had about flutter. Right, there's a lot of data points here. I actually don't recall how many I used. But when we zoom in, right, you see that the spectrum gets kind of choppy here. That's because there are basically, this is plotted with lines, but there's basically a point here and a point here and a point here and a point here. And they happen to get more spread out because this is actually logarithmically spaced, I think, in this calculation, maybe, or maybe in this plot. But anyway, the reason why it looks all jaggedy here is there's just the resolution of the FFT, or the number of points that I used. But it's fine enough that we can see the spacing of these signals, right? So we definitely see the difference between 60 hertz and 50 hertz. But if we wanted to resolve like 51 hertz and 50 hertz, that would be very hard to do. We'd need to pick more points in the FFT to do that. So, and last thing I'll say is usually it turns out that n will be a power of 2. So for example, it'll be like 128 points, 256 points, 512 points, and so on and so forth. So what I'd like you to do is now look at your dynamic signal analyzer in the MyDAC DSA program. And you can observe, now that you look at it, you'll be able to see that there is a thing where you can choose the sample rate, and when you look at the spectrum, it will not show you any data that's faster than the Nyquist rate. So if your sample rate is set to 10 kilohertz, it's going to show you a spectrum that goes up to 5 kilohertz. And then there's also a thing there which includes the number of points that are used to calculate the spectrum. And so now you know that that's this number n. Okay, so do take a look at that and look at the DSA, and now you'll appreciate a little bit more of what's going on underneath the hood. Okay, see you.